All right, so here's where we left off. This is our model NMR spectrum. We started talking about more downfield, further to the left means that less electron density. Right? And we see that different functional groups show up in very specific areas. And you'll notice there's a lot of kind of splitting hairs. Like the hydrogen attached to an oxygen has a really wide range, anywhere from 0.5 down to 5. But then again, the hydrogens attached to the carbon that has an OH attached to it show up in a very narrow area. And they will show up as two different signals. Alcohols are kind of weird in that because it's an oxygen attached to a hydrogen, sometimes they actually don't show up at all, and they don't have the same peak splitting. Here's just another example of when I was talking about the integral of each signal winds up being proportional to the number of protons. So the actual units we get on the area under the curve are meaningless. But the area under the curve is proportional to the number of protons. So we can compare these peaks to each other as long as they're in the same spectrum. We can't compare this integral to the one on the previous spectrum. Right, so that doesn't work. But so it's always going to be relative to each other. But since we know we're talking about hydrogens, we know that there has to be whole numbers for each of these. So you basically, when you find the integral of any of these, you just say, okay, here's my smallest integral. I'm going to call that 1. And you measure everything else relative to that. And so sometimes it's not necessarily, it doesn't necessarily give you these numbers. If it doesn't give you the numbers, then you would actually look at it and you can physically measure the distance. Or what I'll do on a test is I would give you these horizontal lines so that you can say, oh, there, that one's two lines, and that one's 3 lines. That way, I can obviously say that there's 1.5 times more of this than that. But we would want it to be in whole numbers. So if you get something that's really even, like, if this is 1, that would make this 1.5. We want this to be an integral. We won't necessarily, or a integer. We won't necessarily just round it. If it's really close to an even fraction, then you do basically multiply by the lowest common denominator. If this is 3 halves and this is 2 halves, multiply everything by 2. So you get 1, or so you, instead of 1 and 1.5, you get 2 and 3, like we did in lecture. And so here's another example. Another way that you see the integral is sometimes it'll just be shown as this red line for the entire thing, and you just look at it and say, okay, well, if I'm going to call that 1, that looks to be the smallest number. That looks very clearly to be really close to 2. 1, 2.5. Right? You basically are just going to go through and measure relative, find your smallest peak and measure everything relative to that. 1, 2, pretty close to 3, right? So you can say, okay, that's a 1, that's 3, that's 2. Is this closer to 2 or is this closer to 3? Or does it mean we need to multiply everything by an integer number by 2 to see get? Then it gets a little bit. That's when having the formula becomes really important, right? Because if you know there's a total of 13 protons, You just need to make sure that whatever numbers you assign for each of the integrals has to add up to 13 at the end. And so going back to this example, if we looked at the integral and we said it's like 2.5, 2.5, 1, and 1.5, we're already pretty sure we know what this is. But if I tell you it's CHM221, then you know that all of those integrals have to add up to 10 at the end of the day. So in that case, 2.5, 1, and 1.5 is not going to make any sense. That adds up to 5. So I know that I need to multiply everything by 2 to get there. Right, so having, this is the other piece of it, it's knowing the formula. Know the formula, especially if you also have an IR and you know the formula. The integral is really helpful for figuring out how many protons are where. All right, peak splitting is the last piece here. I mentioned this before. Basically, how your signal shows up tells you a lot. And this happens basically because if you have, it's because of what's called coupling, or basically if you have protons that are part of one signal, the protons nearby it can influence their magnetic field as well. They can also be aligned both with the applied magnetic field, or both against it, or one with and one against. So basically, if there are two nearest neighbors, there are 3 arrangements energetically. There's really 4 arrangements, but because these 2 are the same energy, they show up in the same spot. And that's how you get this sort of bell curve shaped, is because this middle one has, there's 2 possibilities where you go one with and one against, or one against and one with, but energetically that looks the same. I'm not going to make you actually draw something like this out, all the possibilities, but this is where the n+1 rule comes from. It comes from this idea that, okay, of the 2 nearest neighbors, they might both be going the same way with the field, both be going against the field, one with and one against. So if you only have one nearest neighbor, if you have no nearest neighbors, there's no coupling with the adjacent carbons, with the hydrogens that are on the adjacent carbons. So you only see a singlet. If there's one nearest neighbor, you get a doublet. If there's 2 nearest neighbors, you get a triplet. And they're always going to have this sort of bell curve shape. It gets the more obvious, the more peaks you have. So, for instance, it's not as good example as I thought it was. Never mind. So here's real data. We know that that's one signal because even though there's a whole bunch of peak splitting going on here, it looks really neat and symmetric and bell curve shaped. So we can look at that and say, okay, we zoom in on that, we see 1, 2, 3, 4, 5, 6. That means that there's a carbon that has hydrogens on it, and those hydrogens have 5 nearest neighbors. So which hydrogen has 5 nearest neighbors? So these 3 are all the same signal, right? So it's not how many things are attached to the same carbon, it's how many things are attached to the adjacent carbon. So these three are all going to show up as the same peak, and they only have two nearest neighbors, so they should show up as a triplet. There's only one triplet on this. So we can be pretty certain that those three are that signal. And all of these pieces should work together. Like we're just talking about peak splitting right now. This is a nice, clean NMR where you can tell the peak splitting really obviously, but the integration and the shielding should all match up as well. Which, looking at this structure, which hydrogen is going to be the most de-shielded? So have the least electron, so be the most partial positive. Yeah, this hydrogen is the most de-shielded because it's attached to a carbon that also has a chlorine. Chlorine's the most electronegative, so it's pulling electrons towards itself. The hydrogens closest to the chlorine should be the most de-shielded. And how many nearest neighbors does that hydrogen have?
That one has 5. Right?
That one has 5. 1, 2, 3, 4, 5. So the peak furthest to the left should be a sextet. 1, 2, 3, 4, 5, 6. And the integral of that should tell us something too, right? Because there's only one hydrogen that's part of that signal. So we should have the smallest integral, the furthest downfield, and the most nearest neighbors. So if it has 5 nearest neighbors, yeah. And this is why we're doing the examples, because we're only looking at hydrogens as nearest. How many hydrogens are attached on the alpha carbons relative to our signal? So 1, 2, 3, 4, 5. So we should see the peak of 6. There's only one hydrogen in our signal, so it should have an integral of 1. So in order, we can think about it just in terms of the smallest integral, and you do the same thing here. And you can literally do this as well if you just use a ruler or side of your pencil. This one very clearly looks like 2. 1, 2, 3, and 1, 2, 3. Right, so all of these pieces should line up with each other. You shouldn't see too much. If you figure it out, you should be able to confirm your suspicions by looking at the other pieces. They're not always going to be this clean, where it's really, really obvious once you know what you're looking at, what goes where. But they should be consistent.
Yeah, so
Mm-hmm.
Like to determine that it's with the bottom on carbon 3 going left to right. Yeah. Is that going to be our
Second, which way? So how many nearest neighbors here?
4?
So it should show up with 5 peaks, right?
So we're going to be like the second one from the left. Yeah.
Yeah, which also makes sense because it's kind of close to chlorine. It's not as close, but it should be a little bit de-shielded. And in general, methyls, primary carbons, are going to be furthest to the right. So this is a really good example because this one can be done entirely from the integration, almost entirely from the integration, and just based on the peak splitting or just based on the shielding. All of those things, you can pick any of the 3 approaches and then confirm it using the other 2.
The number of pages, it's always like 4 acres, 5.
Yes. Exactly. That's what we call that N+1 rule. And that's really consistent as long as your nearest neighbor is not an oxygen or a nitrogen. When you have oxygens and nitrogens involved, that throws things off because the energies are slightly different. So those don't show up in the peak splitting.
Great, because we're only counting the ones that was.
We only count the ones that we're seeing. And even though carbon and oxygen and nitrogen all have even numbers of things in the nucleus, the fact that they have different masses and different charges changes what the frequencies are. And so you don't see the peak splitting on the hydrogens attached to them. We're just looking at hydrogens, and for peak splitting, we're just looking at hydrogens that are also attached to another carbon nearby. You're looking a little rough, right? Are you hanging in there? Okay. I know.
Sometimes I'm like sick. Okay.
So this peak was the most deshielded and also the most peak splitting and also the smallest integral. That's a lot of things. These hydrogens have 4 nearest neighbors, so it shows up as 5 peaks in the signal with an integral of 2 and more deshielded than the 2 methyls. The 2 methyls are going to be the closest in terms of shielding. They're going to be the most shielded. But then just looking at, without even looking at peak splitting, which of these should be more deshielded? Deshielded is most partial positive of the 2 methyls. So furthest to the left.
That's this
Yeah, it's closer to the chlorine, so it's more deshielded. The chlorine is stealing more of its blankets. Right, that's really what we're talking about, shielded and deshielded. Shielded, they have all the blankets. Deshielded, something is stealing their blankets. Correct. The closest to the chlorine is the most electronegative thing here, so it's the blanket hawk. They tend to also be good leaving groups because they're not good at sharing electrons. That's all connected to electronegativity. Things that are more electronegative tend to be more stable on their own, and they also tend to be bigger blanket hawks. So, good connection. Yeah, they don't care about anybody else as long as they get theirs. And that matches with what we see with the splitting, right? Even if we didn't know, if we were saying, okay, I'm going to go based on the shielding, I'm pretty sure that this signal is the methyl that's closer to the chlorine. And then we use the splitting to confirm that, because this one is 2 peaks, which means 1 nearest neighbor. That's these 3. All 3 of these together have 1 nearest neighbor. This methyl group has 2 nearest neighbors, so it shows up as a triplet. It's all well and good as long as I have the structure up there for you, right? But this is exactly why we start with, I'm going to draw 7 possible structures. I'm going to draw every possible structure based on the formula and based on the IR. And then this makes it really clear, makes it easy to eliminate a bunch of them really quickly. Because if you have something in the aromatic region, but some of your structures aren't aromatic, you can just get rid of them. Or vice versa. If you think you have something aromatic, but there's no peaks showing up here, then it can't be that.
The aromatic peaks are also going to be very sporadic.
They tend to be, but they can also, if you have a lot of benzene ring. So for instance, if I had something that looked like there's a lot of symmetry there, right? Really, those two hydrogens are going to be the same signal, and those two hydrogens are going to be the same signal. And they're going to be pretty separated because you've got something electronegative on one side. So you can wind up the signal in the aromatic region for this one, I would expect to look something like pretty neat still. Almost like two very separate signals. They might be kind of on top of each other, but they're definitely going to be in that aromatic region. So you really see it look like a mess when you have an odd number of them, because then you wind up with all those different peaks on top of each other. It's also possible to have an aromatic ring where even though it has 4 protons, all of the protons are identical to each other. If all the protons are identical to each other, they'll all show up as one signal. So your integral will be 4. It'll be in the aromatic region, but it'll be really clean, maybe just a clean doublet. And a clean doublet in this case because that all of these hydrogens are identical and they all have exactly one nearest neighbor. So we might just see a really clean doublet in that case. So it's not always going to be messy, but you don't need to worry too much about the peak splitting on the aromatics because it's more about where it shows up and what the integral is. It's going to be where you get most of your most reliable information. So one of the other ways that I like to, I'll tell you this now, one of your questions on the in-class test is going to be, here's a structure, give me a drawing of the NMR.
Okay.
You don't have to get it perfect. I'm not going to go out and measure the actual chemical shifts or anything. You just have to say, okay, it's going to have this many signals. There's going to be this kind of peak splitting in these rough areas, and I'll give you the table of frequencies. So for starters, let's just see what is, and when I say multiplicity, what's the peak splitting?
Yes, indeed, but
Peak splitting, how many peaks show up in the signal?
for now, public business will figure out on that one. Just
Exactly. Bingo. And that'd be part of what we fans to fill the space. If we had to take one of those that's already compressed and then cut it, then we'd still wind up with the issue of stuff getting around the outsides of it.
That's true, yeah.
So I think this type of cotton works, and we might even be able to go without. In theory, you can do it without the copper wire. You can just wedge it in there, push it down to where it's all in one spot, and then the pressure with the side would take place more or less. Then we don't have to do anything out. So, all right, where are our hydrogens here? We got.
yes. Right.
Now I'm gonna color code them though. How many signals should we, oh, I missed one.
Oh, I missed that one.
How many different signals should we see? How many different protons can we tell the difference? And which means basically how many different carbons have hydrogens attached. That's how we know if they're different or not. So these 6 are all going to be the same, right? They're all identical methyls. These are all going to be the same too.
And then 2 and 2.
And then 2 and 2. Oh, I already used that. Where's my 3? This is the problem. I know it looks better for Instagram if you put all of your markers on both sides up,
But
but then the ink drains. Yeah. The constant battle with Valence and Laura at my house because they like them that way, so you can see the colors and they look pretty.
wait, I still have it in my pencil case so that when I have it in my backpack, they'll drain down.
My advisor in grad school was so picky about markers. If you stood there with the cap off the marker to talk, he would actually walk up and put the cap on for you. So yes, it's definitely a chemical engineer sort of problem.
Both be green.
No, because the red ones are 1 carbon away from that, so they're different from each other. Orange is going to be different than blue because these ones are, we've got 2 methyl groups that are each 2 carbons, 1 carbon away from the carbonyl versus 3 carbons away from the carbonyl. They all look like, yes, they do all look like chicken feet now. But if you had this molecule, we could actually draw. So, okay, we know we should be getting 1, 2, 3, 4, 5 proton signals.
Yes.
And we know roughly in what order they should show up in terms of shielding as well. Methyls are the most shielded, so the blue and the orange should show up furthest to the right. And then the green and the red should show up after that. And then the purple should show up, would normally be, expect that to be furthest to the left. Okay. All right.
Orange.
Orange. So it should go, the order should go something like, this just says, what's the multiplicity of each? But I'm doing the full problem. Like if we were trying to make up, what would we expect the proton NMR to look like? We would expect blue to be furthest to the right, because blue and orange are both methyls, they're both primary, but blue is further away. So say 0 is right here. Again, on the final, I'm not going to expect you to get the numbers exactly right, just the order. So blue, then orange.
Okay.
And then what next?
Green.
Green. Then out of these 2, they're both the same distance from the oxygen, but the secondary carbon is going to be, it's more stable as it's going to be further to the right. So red, and then purple. So that's two of the four pieces of information that we can get from an NMR, right? It's number one is how many signals. Number two is what order from right to left. Then there was the integral. For each of these, we can figure out the integral too, right? Because if this one has an integral of 1, these ones should both be twice that size. Roughly, trying to leave myself room. The orange one should be an integral of 6, so 3 times bigger than that. And again, that's as long as you put the numbers with it, that would be good enough. I don't expect you on the tests to actually get out a ruler and measure it. You could if you wanted to.
Is it okay if we consider that to right? So we're not saying-
Whatever works for you. It's more about this. I don't care as long as they're in the right order relative to each other. Think about it whichever order you want.
Like I would still be, I would have still done the purples versus like that, but I would just start in purple.
Yeah, totally fine. And the last piece is the splitting. What do the peaks actually look like? What's the splitting going to look like for the, let's do purple. We'll go left to right. It has 6 nearest neighbors. So the peak should look something like 1, 2, 3, 4, and then just mirror it. And we would say that that's a multiplicity of 6. 6 nearest neighbors. Actually, sorry, we'd say that's a multiplicity of 7. So multiplicity is the number of peaks, not nearest neighbors, technically. I don't get hung up on that though. Why it's useful is the nearest neighbors. What's the multiplicity for the red one? How many nearest neighbors are there? Does that affect anything though?
No.
Just the nearest neighbors. So even though there's 2 of those, they're not interacting with each other because they're identical. The ones that are on adjacent carbons interact. So that would give us a multiplicity of 3. So we see a triplet. And again, the nice thing is if you're writing out the integrals separately, it doesn't matter what the height is. Make the height whatever's convenient for you to draw. What about green? How many nearest neighbors?
2.
Just 2. So multiplicity of 3 as well. You should see another triplet.
But we already knew that. that those are gonna be the same because they know those two is good.
Those are telling us two different things though.
Oh,
This is telling us how many protons are in the signal. This is telling us how many protons are nearby the signal. So they happen to be the same in this case, but they're not always. How about the orange ones? How many nearest neighbors? One nearest neighbor, just the purple one. So the multiplicity then is 2. So we just see a doublet.
are those the same size?
And they'll both be the same size, roughly.
Like those have none,
No nearest neighbors.
so they have one.
So it's just a single peak, singlet. So if you're systematic about it, it's actually easier to answer this type of problem than it is if I give you a real spectrum and you have to guess what the structure is. Because there's 4 pieces of information here. Number of signals, order of signals, and roughly where they show up. The integral and the peak splitting. I don't have my handy. Erase all marks option when I'm using an actual whiteboard. So this is the same one we started. It doesn't have the integral drawn. It doesn't even give you the structure. We know we have benzene ring. So draw a benzene ring. We're trying to figure out what our possible structure is. We know that that's a benzene ring. We don't know how many things are attached to it or where, but we know we've got a benzene ring. All the way down here by 1. Furthest to the right, so we went back to our table of frequencies. We'd see, okay, anything close to 1 is going to be a methyl group. So we say, okay, I know I've got a methyl group. This one's in a range where it could be tertiary carbon or hydrogens on a tertiary carbon or a secondary carbon, but the peak splitting tells us what?
Wow.
You know, it's got 3 nearest neighbors. We know that, and anytime you see 3 nearest neighbors, 3 is a really convenient number for it to be a methyl group. We know we have a methyl group. We know we have something with 3 nearest neighbors. And we know our methyl group has 2 nearest neighbors. So if you have a methyl group with 2 nearest neighbors, there's only one way that can happen, right? Because the methyl group has to be attached to only one other carbon. If you have a methyl group with 2 nearest neighbors, you've really got an ethyl group. Right, so you start to see some of these patterns. So if we know we've got an ethyl group and we know we've got a benzene ring, what's the most obvious structure we could draw?
Benzene.
Benzene ring with an ethyl attached. And that is going to match That makes this make sense then, right? Because this CH2 then doesn't have any other nearest neighbors. If this was a pentuplet instead, then it would have 4 nearest neighbors. That throws this out the window because now all of a sudden our splitting doesn't match up with our structure we tried. So some of NMR is throw stuff at the wall and you see what sticks. Okay, this is technically possible. Can I rule it out? And once you've ruled out everything, you can end with 2 possible structures because sometimes I don't give you enough information to get all the way to your final answer, but you should be able to get down pretty close, down to a couple of options. Right? Because most of the possibilities won't match something. Now, if we took IR of the same molecule, and it showed that there was an OH group. Well, that would be weird, but without more information, it might technically be possible. We could have this. The benzene ring gets all clustered anyways. And OHs, these hydrogens don't always show up. Because the oxygen is a different nucleus than carbon, and it causes different interactions. It definitely won't see any splitting on this one. Even if there were nearest neighbors, OHs don't split. I'm just giving you as an example, like, okay, as we find new information, sometimes what we think we had, we need to amend it somehow. That's the scientific method, right? You think you've got a pretty good understanding on things, you test it, something's a little bit weird. And so you have to adjust things. So this is the right structure for this. And I'm not going to expect you to remember all of this the first time you do any of these. Okay. That's why you have notes and recordings. All right. Should we do one more example all the way through, or should we start working on the lab and come back to this in a little bit? Okay, deal. Let's do it. I'm going to stop recording. And we'll start playing around with chemicals.